Hi everyone, in this video we're going to start taking a look at density curves, which will lead us to the normal distribution, which will lead us to the 68, 95, 99, 7 rule. You can read the learning targets now, but they're all to do with density curves, mean, median, and eventually to the normal distribution. Let's get right to the activity. What we want to do is explore what are called density curves, and the idea behind density curves, we're going to do 3 experiments, and each of those 3 experiments, it's really important that we understand that we are doing each of these experiments many times, more times than is feasible than to do in class. So when we make our prediction in a few minutes, it's important to note that you're making a prediction about what this will look like if we do it many times. So the 3 experiments we want to do, we want to roll a 6-sided die many times. We want to toss a penny and make it land on a target many times, and measure the distance from the center of the target to the penny. Finally, we want to try to stop a stopwatch at exactly 5 seconds and record what the stopwatch actually reads. So what I'd like you to do is pause the video and try to make a prediction for what the graph of each of these things is going to look like. So why don't you take a minute, and hopefully by now you've had a chance to lay out what your prediction might have looked like. And so what I have, instead of a prediction, what I have is what an actual classroom experiment looked like in the past. And so we had many students perform each of these experiments many times. How many? Many. You know, between a couple of classes, trying them a bunch of times, we had a couple hundred trials. And this is what our experimental data looked like. And I'm going to leave the actual for what being able to do that experiment an infinite number of times looks like. It's impossible to do this experiment an infinite number of times, but theoretically, it actually gives us a really good idea of what a density curve is going to be if we can imagine doing this experiment in an infinite number of times. So if we do this experiment, if we roll a die an infinite number of times, what's this curve going to look like? Well, the curve is going to be a straight line straight across and straight down, the same height the whole way across, right? And so what that means is that 1, 2, 3, 4, 5, and 6 are going to occur equally likely. So if you do this an infinite number of times, the frequency bar eventually evens out. It converges onto that same value. And so now let's imagine for a quick second, where do you predict the mean and median to be? Well, what's the average value of 1, 2, 3, 4, 5, and 6? It's going to be right here in the center around 3.5. And in this particular case, this is symmetric data, so the mean is going to be approximately equal to the median. Next, let's look at what happened when we tossed a penny many times and measured the distance to the center of the target. What you'll see is you have a lot of values close, and then as you go farther and farther away from the center of that target, you get fewer and fewer values. That would, of course, be a skewed data set. So let's draw that as a curve now. Okay, skewed. This is clearly a skewed right. And so how does that dictate the relationship between the mean and median? Well, the median would, let's just say, about here. And where would the mean be? Well, the outliers over here would pull the mean to be larger than the median. That's that whole resistant versus non-resistant values. And finally, your stopwatch. Again, the values seem to be clustered around the center here. The most values occur between 4.96 and 5.04, which means the 5 is going to be about the average, right around the middle. And so this is definitely a symmetric data set. If you tried to smooth that out, like lay a blanket, can you lay a blanket over that data and kind of smooth it out so you can see the shape? And this is going to be a symmetric data set. And the mean and median are going to fall right around the center there. And we always use that approximately to soften things, to give ourselves a little bit of leeway. All right, so now that you've had a chance to take in all of the information on these 3 experiments, the stopwatch experiment led us to something called a normal curve. Normal curve has this nice bell-shaped curve, and let's look at how our data is related to that. So of all the submitted data for the stopwatch, the sampling mean was 5.01 and the standard deviation was 0.4. What we want to do is fit the mean and multiples of those standard deviations onto this bell-shaped curve down here. So 5.01 would live here in the center, and we've got some markers for 1, 2, and 3 standard deviations both above and beneath. So why don't you go ahead and pause that video and see if you can fill those in. And I'll do that from here. So we've got these values along the x-axis here, marking where 1, 2, and 3 standard deviations both above and beneath the mean occur. And I'd like you to look at these 4 questions, but be sure to put the word approximately before each of them. So approximately, what percentage of the data is within 2 standard deviations of the mean? So let's take a look at this. So in this example, in this experiment rather, what percentage of our data that was submitted lives between 4.61 and 4.21 and 5.81? Well, most of it, right? So exactly what percent? We don't know yet. Because all we have right now is approximately 1%. We would need every single data value to calculate what percentage. So what percentage is further than 2 standard deviations from the mean? Well, whatever this percentage is, it's whatever's left over. So data is either within or without 2 standard deviations, right? Within or outside of. So let's take a look at what's called the standard normal curve and figure out what percentage of data lies within a certain number of standard deviations of the mean. So here is our standard normal distribution. And with the standard normal distribution comes something called the 68, 95, 99, 7 rule. And what that is saying is that 68% of normally distributed data falls within 1 standard deviation of the mean. 95%, remember, most 95% of data falls within 2 standard deviations of the mean. And you guessed it, 99.7% of data falls within 3 standard deviations of the mean. Let's get a little more specific. If 68% of the data falls within 1 standard deviation of the mean, that means that 34% falls below and 34% falls above within 1 standard deviation. So how much falls between 1 standard deviation and 2 standard deviations? So we've got 13.5% here and 13.5% down here. How much falls within 2 and 3? So we would then do 99.7 minus 95 over 2. 2.35%. And 2.35% here. And finally, how much falls outside of 3 standard deviations? Well, what's left over? 0.15%. Fix my handwriting there. 0.15% down up there, and 0.15% down here. Now, it might look like 0 because it looks like the curve touches the line, but just be careful. This curve doesn't quite touch the line. There is a horizontal asymptote here because it is always possible for one single data point to fall very, very, very high up the ladder and many standard deviations above the mean. You know, uncommon, but possible. So just do understand that there's an asymptote living there. And so that 68, 95, 99, 7 rule is going to really set the stage for much of the rest of the year. With that said, let's go ahead and debrief on the important ideas from this lesson. All right, so here's the foundation of the important big ideas that we discussed in this lesson. So the 3 experiments gave us some insight into density curves. And a couple things about density curves. They're always on the x-axis, and the area is always equal to 1 under the density curve. So when we looked at this thing, the area of this whole density curve was equal to 1. All right, so given that, what's the width of this thing? Width, let's go back to geometry, is 6, and the height would therefore be 1/6. And that represents the probability of getting a 1 is the height above 1. The probability of rolling a 1 would be 1/6. The probability of getting a 4 would be 1/6. That height helps represent the probability of a given event happening. And that's how density curves work. So this is called a uniform distribution. If the width is k, the height therefore is going to be 1 over k. And that's an important feature to think about. The next thing we looked at was what happens with the mean and median in skewed versus symmetric data. This goes back to different kinds of resistant values. So now think about it for a quick second. The density curve, remember, is an area of 1. So the median is the value that makes half of the area on one side and half of the area on the other side. 50% below it, 50% above it. So where does the mean fall in right skewed data? Remember that the mean would be greater than the median in right skewed data. In left skewed data, remember we're going to have the median right around here, and then we get the mean a little bit lower. Remember, it would be pulled down by those outliers. So in left skewed data, we're going to have the mean being less than the median. So when we look back at this one here, this was skewed right. So therefore the mean was greater than the median. When we have symmetric data, the mean is always going to be approximately equal to the median, regardless of whether it's a bell-shaped curve or it's got several humps, peaks like a camel or something. Any way you look at it, the mean is going to be approximately equal to the median, and that's what we saw with our stopwatch experiment that led us into the standard normal curve. The normal curve, there's a lot of data on the normal curve to fit in just our little bit of a box, but we'll call this our mean. And 1 standard deviation, 2 standard deviations, etc. We have that all detailed on this page, so we don't have to go too crazy on that. But what goes the important takeaway from the normal curve for this particular, for this box is the 68, 95, 99, 7 rule, and that is the percent in a given area. So take a few minutes and look at the check your understanding problems, and I'll add your answers and talk about them a little bit. All right, so let's review these check your understanding problems. Hopefully you've had the chance to do them. So for internet reaction time test, we've got a uniform distribution where a flash happens somewhere between 1 and 5 seconds. So the width of that density curve is 4. Since the area under that width needs to be 1, the height rather needs to be 1/4. So about what percentage will be greater than 3.75 seconds? So what you need to do is figure out the width from 3.75 to 5, which is 1.25. Then multiply that by the height and figure out the percentage of the time 31.25 will occur greater than 3.75 seconds. Last thing, calculate and interpret the 38th percentile. Going back into chapter 1 a little bit, the percentile is the data value where 38% of the population is either at or below. So you need to figure out the width that creates an area. So geometrically, you need to calculate the width that creates an area of 0.338. So just a quick little algebraic, 0.38 equals 1/4 of W, W 1.52. So the width, the blue width here is 1.52. Its relative location would be 2.52. So 38% of the time the flash will go off before 2.52 seconds. That would be the 38th percentile. One word on number 2 before we go too much farther. This little lowercase mu is a Greek letter. We will use that for the population mean. And the Greek letter small sigma will be the population standard deviation. So S is the sample standard deviation, X bar is the sample mean. Mu and sigma are the population standard deviation and mean. So with that said, we can label this as a normal curve. First things first, let's make sure we label this thing. When we draw a normal curve, we do want to label it with mu and sigma. So if we go back to our standard normal would be N01, labeling the mean and standard deviation. So label that and then count the different standard deviations above and below the mean, and then you're all set. Using those now to compute some percentages, what percent of young women have heights less than 69.5 inches? Here's your 69.5 inches. So everything less would be everything to the left of that. So you can do it one of two ways. You can add up all of the different intervals that contribute to up to there, or my preferred method is to do less work, add up the two values to the right, subtract them from 1 to get 97% either way. Finally, is it unusually short in this distribution to have a young woman who is 62 inches or less? Not unusually short, because 16% of young women have that height or less. 62% is at the 16th percentile. So I would wager that that is not unusually short. Let me know if you've got any questions or comments about density curves or the normal distribution.